This week we're starting the first of two lectures on electrochemistry. And whether you believe it or not, God does commend His love toward us in that while we were yet sinners, Christ died for us. I know when we talk about things like electrochemistry, you begin to wonder about God's love. But believe me, He does love us. Electrical chemistry is important in many things, but one of the most obvious things is the electric vehicles. These vehicles contain batteries that generate electricity and also can be recharged using electrical energy and using electrical energy to convert a chemical change and then a chemical change to produce electrical energy. And so we use batteries everywhere, and these batteries are put together in such a way that they take advantage of electricity produced by chemical interactions. And we'll talk about the first part of this week, and then we'll talk more specifically about batteries next week. Electricity-related phenomena include things like lightning, static electricity, and the current produced by a battery. A galvanic cell, or a voltaic cell, is a device where the spontaneous oxidation-reduction reactions produce electricity. And that's what we're going to focus on today, is galvanic cells and how they're set up and calculating the amount of voltage that can be produced. The site of oxidation of a galvanic cell is called the anode, and it has a negative charge. It is the site of oxidation, and it's the site of the oxidation reaction that we will be writing. The cathode is the site of reduction, and it has the positive charge. So the anode is the negative, the cathode is the positive. The anode is where oxidation occurs, the cathode is where reduction occurs. So when you put a clean piece of copper wire into a clear solution of silver nitrate, an oxidation reduction reaction begins to occur. And when this happens, there's an exchange of copper ions for silver ions in the solution. As the reaction proceeds, the solution turns blue because the copper iron's present and the silver metal is deposited on the copper wire that's placed in the solution. Now here's a picture of what's of a stylized or a sort of ideal galvanic cell, and it sort of is a stylized version of what you saw on the previous slide. You have on the left here, you have a solution of copper nitrate which has copper ions. You have a copper strip, and because this is where the oxidation occurs, this is the anode, and it has a negative charge. At the same time, on the right, you have a solution of silver nitrate with a strip of silver, and because this is where reduction occurs, when oxidation occurs, the copper ions are released into the solution. When reduction occurs, the silver metal is plated onto the silver anode or cathode. And in the process, there's a flow of electrons, which produces a certain amount of voltage in the voltmeter. And similarly, during this time, you have the floating of cations in one direction and anions in the other direction through the salt bridge. And the salt bridge is also what completes the circuit. So the cell potential is created when two dissimilar metals are connected and is a measure of the energy per unit of charge available from the oxidation reduction reaction. And a volt is equal to the joules divided by coulombs. Joules being the energy and coulombs being the charge involved. So a positive cell potential indicates that there's a spontaneous reaction, that electrons are flowing from left to right. Electrons are flowing from left to right. in this standard galvanic cell, the half cells are separated. That is, you have the copper on one side and the silver on the other side. Electrons can flow through an external wire and become available to do electrical work. So, in a sense, this is a battery. So, electrons flow from the negative anode to the positive cathode. So, from left to right. Oxidation occurs in the anode, which is negatively charged. And here's the equation where of the oxidation. Oxidation, remember Leo, it loses electrons, so it's oxidized. Reduction occurs at the cathode, which is positively charged. And again, remember, gains electrons, gains electrons, reduced. The cell potential is a result of the inherent differences in the materials used. That is, this voltage is a result of the difference between copper and silver. And the salt bridge is present to allow or to complete the circuit. You cannot have flow of electrons without a complete circuit. Now, there's a standardized way of writing there's a standardized notation for writing the when you make a cell, and that's called cell notation. It's a shorthand that provides information about the various parts of the cell. Active electrodes are the parts of the cell that actually have either oxidation, in this case on the right or on the left, or reduction going on. So the active parts are part of what's in the notation, but then there are inert parts or inert electrodes. They are things that are in the cell but do not participate in the oxidation reduction reaction, and they merely act to complete the circuit. In this case, the two cells, on one side you have the oxidation, magnesium being made into magnesium ions. On the other side, it's hydrogen ions being made into hydrogen gas. But since hydrogen gas bubbles, you have to have a solid to conduct the electricity. And in this case, they used a non-reactive platinum wire. So the non-reactive platinum wire acts as an inert electrode that allows for the formation of the hydrogen gas. So the oxidation of magnesium occurs, and the magnesium produces magnesium ions, and this occurs on the left. The reduction is hydrogen ions being made into hydrogen gas, which occurs on the right. The inactive electrode, which is on the right, is the platinum wire that allows the electrons on the left to pass and move to the right. So the overall reaction is shown: magnesium plus hydrogen ions forms magnesium ions plus hydrogen gas. The notation is shown underneath it. You have the anode, the oxidation side on the left, a double bar, the reduction side of the cathode on the right, and then to show that there's a inert electrode, you put this little platinum symbol outside and that shows that you have to have this inert electrode on the cathode side. So if you consider the following redox reaction, you have chromium is oxidized to chromium ions and copper is reduced to copper solid. Write the oxidation reduction half reactions and then write the reaction using cell notation, which reaction occurs at the anode and the cathode. Well, let's take a look at this. So the oxidation is the chromium. Chromium loses 3 electrons per atom, so a total of 6 electrons. It loses 6 electrons and forms chromium ions. So it's losing electrons, so it's the oxidation side. The reduction side is the copper. It gains 6 electrons to form 3 atoms of copper solid. This would be written this way. In the cell notation, you have the chromium on the left, the anode, the copper on the right, the cathode. And then if we look at a second reaction and we look at the same question, iron reacts with hydrogen to form, and you see that what happens here is iron is oxidized to form ferrous, to form ferric, or iron 2 to form iron 3. At the same time, manganese is reduced from a +7 to a +2. So your half reactions look like this. You have 5 iron plus 2 goes to 5 iron plus 3 plus 5 electrons. So you lose 5 electrons from the 5 iron plus 2, and that is oxidation. At the same time, manganese gains 5 electrons to form manganese plus 2 plus 4 water molecules. Now, since the manganese and the iron, neither of those form a solid, you have to have these inert platinum electrodes in there to mediate the whole reaction. And so it's shown that the platinum electrode on the right, or on the left, is the oxidation of iron plus 2 to iron plus 3. On the left, you have the manganese going from manganese plus 7 to manganese plus 2. And both of those require a platinum electrode. Now, in order to do these calculations, they had to do something called a standard, or set up a standard. And in order to do a standard reduction potential, they had to start out with what's known as a standard electrode. And basically, by convention, they decided to use what's shown here as the standard electrode, which is the conversion of hydrogen to hydrogen gas. So the reduction of hydrogen, it was decided that this would represent the standard electrode. So the standard hydrogen electrode is the electrode that was assigned the value of 0 and is the reference electrode for which the potentials for all other elements are determined. And the reaction is as follows. A 1 molar solution of hydrogen ions forms hydrogen gas at 1 atmosphere. So then these standard conditions with this standard electrode, they determine, or they arbitrarily set this as 0 voltage. The potential of this reaction is 0. So hydrogen gas at 1 atmosphere is bubbled through a solution of 1 molar hydrochloric acid. Platinum, which is the inert electrode to the action of the hydrochloric acid, is used as the electrode, and electrons from the surface of the electrode combine with hydrogen ions to produce the hydrogen gas. And the electrical potential for this reaction was assigned as 0.